So the root test is very similar to the ratio test, but sometimes it's more beneficial to do one over the other. Generally, when you see powers, n variables, and the exponent of a certain expression inside of the series, it's beneficial to use the root test. But the idea behind why the root test works is the same as the one as to why the ratio test works. So basically speaking, if you have this limit, then that means that for a large n, the nth root of an, and again, I'm pretending an is positive just for the sake of it, it's approximately L for very large n. I can raise both powers, both sides, to the power n to get this as approximately L to the power n, which means this is geometric approximately with the ratio L. So again, if L is 0.5, then this is, or maybe 1/2, this is 1/2, 1/2 squared, 1/2 cubed, 1/2 to the power fourth, and so on. And so this is going to converge. And again, absolutely, because I'm taking absolute values here of an. And L greater than 1 means it diverges because geometric series with ratios greater than 1 do that. And whenever L equals 1, then the test is inconclusive for the same reason as the ratio test was. And that's because we can have some alternation going on. So it is unsure what to do here. Just have to use a different test. So very short video on this. Here are a few examples. You can see what I was saying before, right? You see some n in here. So you can see that canceling out this n would allow you to very easily find the limit of whatever comes inside. So when that's the case, you can go ahead and try the root test, see if it works. So for A, I'm going to do the limit of the nth root of absolute value an, and n goes to infinity, that's the limit. N goes to infinity of the nth root of n squared over 2n squared plus 1. All of that to the power n. The nth root and the n power cancel out. Everything here is positive. There's no issue. And so I'm doing this limit. I can show my work by dividing by n squared, but I know this is 1/2. And so this is less than 1. So that means the series is absolutely convergent by the root test. So you can see the trick was getting rid of this n. And also one thing that students get confused when they see this solution here is whether the limit being 1/2 not equaling 0 is not supposed to tell that the series diverges, but that usually happens when you're getting the test for divergence confused with the root test. Each test has its own criteria. On the test for divergence, you take the limit of the thing as it is, and the thing as it is doesn't have a limit of 0. It doesn't have a limit of 1/2. The thing as it is has this power of n. It will be 1/2 to the power of n approximately, and that will go to 0. So the test for divergence is inconclusive here, but the root test is not. It tells me that the series does in fact converge. So let's do B. B has some negatives in here, and so I'm going to use the absolute values as well. So I'm going to do limits for B. Doesn't bother me at all because absolute values just allow me to cancel everything out. In terms of the negatives, I mean. So again, I can rewrite the inside, the ANs with absolute values, get rid of the negative as 2 over n to the power n. Then taking the square root of that again, The square root and the power n cancel. This is the reason why I would choose to use the root test on these. Excuse me. I get those confused at times, so I may be saying the wrong words now and then. And that is clearly 0. So again, this series is absolutely convergent. And the last example that I'll do today is C up there. 1 plus 1 over n squared. And this is another one that's sort of relies. You see this n squared. This is a bad power to handle this limit with. If you take the nth root of this, you'd like to cancel it, right? But not both n's go away. Only one of the n's goes away here, and you end up with this limit. And that is, again, a known limit. That equals e. This is known. And e is greater than 1. So that means the series diverges. If my series had some alternation here, if it had some alternation, then I'd have to be careful as to also check whether it diverges without taking absolute values, because the root test allows me to take absolute values here. I take them, and I see that it diverges by making all terms positive, but if I had allowed the series to remain alternating, then maybe it would converge. Right now, that's not a problem. Just something to keep in mind for future applications, but I hope that made it clear. Root test is pretty simple to apply as long as you understand how the rules work.